I think that majority of the guys who are here are developers, right? What I heard. Okay, I think the presentation will be quite interesting for you. It's more technical and I think enough complicated. So we talk about mastering Onchain asynchronous development. First of all, we will discuss about what is asynchrony, what is in general cross-chain development, and a bit of real code, asynchronous code on-chain. That's probably not very usual for the developers on Solidity. Okay, let's start from the simple understanding of asynchronous versus synchronous execution. Yeah, probably if you're from Web2 or just normal development, you understand what is synchronous and asynchronous execution. But briefly, in synchronous execution, if you have two processes, when you actually invoke the function actually stops execution and pass the instruction pointer to next process. That means that if some flow executed on process A, when you call a function, it jumps to process B. In asynchronous development, the execution on the process A continues. So you can have the simple analog from the chains. If you have execution on chain A and chain B, in synchronous cross-chain architecture, you have this break, and chain A awaits of the finishing the process on chain B. At the same time, asynchronous is more natural, and what we have at the moment, when you actually want to invoke function on another chain, it's asynchronous. So, but we also have a concept. A concept of atomic and non-atomic execution. That's also probably what you heard a lot from Vitalik, from Dankrat, and the guys from Ethereum Foundation. The idea of atomic means that some execution is not reverted, non-atomic, if the following instructions failed. A simple example is your CPU flow. If some of the instructions in your CPU fail, it doesn't affect the previous one or the state of your CPU. At the same time, atomic execution requires reverse changes to some point if the failure happens. For example, the transaction on DB. If you commit transaction in your DB, that means if it fails on some intermediate stage, all the changes done will be reverted to the stage like when the transaction is not executed. Oh, sorry, okay, this. So, but let's back to cross-chain system. What I mentioned, actually, we have asynchronous execution across chains. Like, for example, if you build your application, let's say Uniswap, and would like to have some cross-chain interoperability, it will be asynchronous, definitely. I mean, ZK Sync era, ZK will not wait until your execution done on Arbitrum or whatever. You have asynchronous execution. And you have a non-atomic execution, of course, because if something wrong on Arbitrum, the revert will not happen on ZK Sync. And that's quite natural. At the same time, in sharding system, you have absolutely the same setup. You have non-atomic asynchronous execution. Long row, but you now understand what this means. So, but the difference with sharding infrastructure as kind of cross-chain system, yeah, because again, like imagine sharding as a just cross-chain system, that you have just extra guarantees. In general, you have just inbuilt communication instead of bridges that you would probably use if you would like to build your cross-chain application. You have inbuilt communication protocol. Also have full chain interoperability. What actually means that if you have two chains, they will be fully compatible between each other. As well, you have extended economic model because again, like you have different economic model between even two different rollups. That sometimes can bring you troubles. At the moment, it's not a big issue, but I think that with new updates of Ethereum economics, it can bring few funny cases. And non-block and synchronous execution, it's same for cross-chain system, but here at least we guarantee that your message will be delivered. Okay, but what we have to talk about in this presentation, first we have to reconsider account model. we have to talk about async calls, redefine tokens, and talk about development patterns. So we actually cover everything you need to start asynchronous development. First of all, we shall not have accounts, classic accounts on Ethereum. Why? Because it's way more convenient if the whole system is just smart contracts. Yeah, formally saying, Ethereum was also shifting to account abstraction and integrates it more and more, but for the asynchronous system, having smart contracts is more convenient than accounts because you operate within the understandable environment for your accounts, for your execution. So this is just a simple example of such smart contract. Instead of verification of your transaction as externally owned account, you have just verified call. I'm as a user sent transaction. It's the signature verified on chain. That means that it's me. So, and I just call the function you wanted to execute on chain. That's the only change for you as a user. And you will even not notice this. Simple. Async call. That's part of the magic. Async call is actually a special call. In general, we implement it as a precompile. Some chains that are now working on cross-chain interoperability, they are doing this as a native part of the protocol. So this function actually just as a simple call, but the only difference here is that it's not blocking. As you can see, you have two functions, not stop here and don't wait here as well. They will be executed straightly after the async call function creates the bundle that will be transferred to the other chain. But we don't wait for the completion of this call. That's the most fascinating part here. This is where asynchrony comes from. And as you can see, the fields of such a async call are quite simple. That's just destination, message sender, value, and your ABI. So that's it. You probably ask where we specify the chain we send it or shard. It's actually in address. If you think about address space that you have across chains, with probability close to 99.99999, you can distinguish address on zkSync, Arbitrum, any other shard, and the chances the addresses will be same, actually close to 0. That's very simple concept here. But what guarantee we have from the bridges, for example, first of all, that messages will be processed and delivered in any way, because they cannot disappear. The messages is part of the shard. That's the difference between bridges. Bridges emit events, and oracles actually grab these events. Messages in general are not grabbed. They are inserted in the block, and all the other peers who are interested in the messages can see it in the part of the block. Also context saving. Of course, if you send a message, you would like to save context. First of all, message sender. I mean, if you send a message, you want on the other chain your message executed like in favor of you. Like it sent me, not the smart contract. So that's why we save a context. Specifically, it's important for a contract that works like ERC20, when you have this message sender. So please consider this. And with bridging, it's impossible because always message sender will be the oracle who relate your message. That's why you have to reconsider the logic. Here you can save the context and actually repeat it from the VM. Refund and gas bounces, that's as well, because if your message failed, you will have refund and bounce, but what you don't have is a bridge actually. Failure on chain notification, if your message failed, you will receive notification on the source contract to the special function that, sorry guy, but this message failed. In general, bridges can provide these, but for extra money. So, and cheap. Yeah, actually cheap, probably. Of course, if the shard is not expensive at the moment. But yeah, message like async message sending is very cheap because actually we don't require any relayers or third party who can charge us extra funds. Why we redefine tokens? That's next question that probably People may ask why we have to redefine the tokens, because we cannot use ERC20 architecture in cross-chain system and in sharding system. The simple reason, the real reason is the third point, because ERC20 has bottleneck. ERC20 is just like a registry book. You have like account balance. Now think about how you can distribute this database across few chains without complicated synchronization, double spending, and all of these pretty beautiful problems. Also, we have to consider that, we don't have atomicity, and the sending can be low, you can be front run, different problems. But yeah, the biggest problem with this registry. Okay, what we have as another option. Another option is what is called enshrined token. The idea is like, if ERC20 is like bank account, enshrined token like a cache. So imagine that now you don't have a single registry, but you say like, okay, some address on the smart contract has specific tokens. And the problem is easy. Now you just don't transfer the record, you transfer the money. So if I would like to, for example, transfer 100 bytes of $100 from you, what I first do, I mean the 100 tokens on the USDC contract that can live on any other chain or shard, I don't care where. But it has unique ID, its address. What I can do now is using the precompile function, like deposit, for example, transfer this amount to the specific address on your smart account. Oh, sorry, smart contract. So I hope the idea is quite clear, because again, imagine that you have some memory space of your smart contract, and only a specific function can put the money there. And this function is responsible just for a simple verification. Okay, this smart contract had this money, and this transaction is okay. So I will deposit from you to this account. Why it's better? Because first of all, you don't have a single point of registry, because every account has money. Now transferring of your money is just a matter of shifting the balance from one account to another. You can ask, okay, but how can I know how much money I have? That's the small disadvantage of this model. Probably you would have to go over the smart contracts you know. But it's not a big deal, because it's on-chain stuff, off-chain. On on-chain stuff, you have the balance on every smart contract. And let's go to the most interesting part, the on-chain patterns. I will provide few quite interesting asynchronous programming patterns on-chain that you can use to develop asynchronous application with these async calls. You can try our sandbox. This is actually close to Remix IDE, but it's a bit lighter, but for the cross-shard, cross-chain development. So we talk about deferred execution, proxy, self-running transactions, and task pools. Probably 3 or 4 you already heard somewhere, so that's why it shall be not very new. First of all, deferred execution. This is one of the basic patterns. Probably those of you who try to ever program in parallel system already faced such pattern. What does it mean, deferred? That means that at the moment when we need async call, we stop execution and just start execution back from this point later when we have results from other shard. That's a kind of async await pattern, but with async and await. So how it works? So you have a full function that first check if the function is updated. That means, okay, if we continue this function or we start from the very beginning. If we start from the very beginning, it's not updated, and we go with this some logic. Then we check if we require some update from, let's say, other chain, receive some data from other chain. Okay, seems like we want some data, so we create a async call, some other function on other shard, and save the context. What is the context? Actually, whatever you want. So context can be your local parameters of the function, memory state, stack state, whatever you want. And that depends on what you consider is the context for your function. And you abort execution from this point. So the asynchronous call continue on the destination shard, and destination shard will process and send your result back to the same function. Same function started okay, but I received an update. Okay, I will not continue updating it. Update required? No, because I just received an update. So if you have the update, we restore the context and continue execution as the function didn't stop. That's it. That's how you can actually easily create a async await pattern without any difficulties. Next pattern. Proxy. Majority of you are familiar with the proxy pattern from the general idea, but here proxy pattern serves different role. Say you are building Uniswap and you decide to do different pools on different shards. Let's say USDC ETH on shard 1 and USDC BTC on different shard. But the user wants to exchange Bitcoin on the first shard, but you don't have this pool. So the pattern, proxy pattern is very simple. What it checks, actually check if the pool exists. If the pool doesn't exist, what you do, you create a sync call to the shard that has this pool. Yeah, because actually you as a provider knows which pool is deployed on which chain. So you create this request, send users money to this shard, and actually stops execution. When the user money will be exchanged on the shard 2 and message will be sent back, it will be sent to the same function, but it's now will be just called send token to origin. So actually just transfer the received token to user. Very simple, but in general very powerful pattern, because now you create a very decent user and developer experience who would like to, for example, integrate your application to their own application, like create really composable application. So very simple but quite powerful pattern. Self-running transaction. This is what you probably never heard, but it's very powerful pattern specifically in asynchronous execution chain. Imagine that now as we can create a transaction to other shards, we can create a transaction to ourselves. Yeah, why not? And what we can do with this, for example, you can run your transaction almost infinite time. Yeah, depends on how much gas you put, how much money, but you can actually send message to yourself so many times as you want. And you don't need to do it manually. It will be done automatically. So here, you have some liquidate position function. Imagine that market is now extremely volatile, like another Trump coin emerged. So we want to liquidate the position, but it seems like we don't know when this position will really go to the threshold of liquidation. So instead of monitoring it off-chain and be happy and pray that we will be first to liquidate it, we create a message that is sending back to ourselves until we have success in some check liquidation as possible. If it's fine, we liquidate the position and we are happy. If not, we continue sending message again and again. And this pattern and all those patterns back comes to probably one of the most powerful patterns from the async world, what is called task pool. Yeah, I think that majority of you ever heard about tasks pool. That means you can now distribute your load across the different shards asynchronously and in parallel. So how this pattern works? First of all, you have some task. In our idea, it's just a counter. Let's say we want to create some parallel counting to some number. You create a task pool created of 10 tasks. We have 10 different contracts on 10 different shards. You start with a run function that actually creates 10 asynchronous calls to 10 different shards. So very easy. We distributed 10 tasks across 10 different shards. Very easy one. And now we have a separate function that actually receives results and just verifies that, okay, task is done. So yeah, at the very beginning, we have task done 0. Then we receive and count how many tasks we finished. and we have await function. That now, this await function we can run as actually self-running transaction. Imagine that you run await function as self-running. So what does it mean for you? You create a run function, execute these 10 asynchronous parallel tasks, and then immediately call await function. And the await function is self-running because we do this address. So we send to ourselves to this function transaction again and again. And what we wait until 10 tasks done, or we wait, for example, timeout. Yeah, because of course, in any asynchronous execution, you have some timeout. In our case, it's 100 blocks. If 100 blocks passed, we just time out the execution and say, okay, something went wrong. And that's it. And with this task, you can imagine, you can do whatever task you want, whatever parallel asynchronous task you would like to have. Yeah. And that's probably it. You can, first of all, try our IMM DEX, also cross-chain, this cross-shard, and see the architecture in more details. And yeah, thank you. Yeah, I'm sorry it can be quite complicated presentation, but I'm ready to answer your questions. Yeah, sure.
So, if I understood correctly, some of the async part was also not just focusing on the ZK sharding, but also like a bit cross-chain.
Yeah, in general, yeah.
And my question would be, why have you thought about setting up this architecture in a way that you have like one proof of source? Let's say you put it on one rollup, and then you treat everything as extensions, because then like some of the engineering solutions that was implementing more complex contracts would be avoided, and then you have like some very sort of stupid contracts as extensions, and then you have like a ledger as a host. It's more, it's a centralized, but it's easier than synchronizing, which you also said is hard.
Yeah, in general, that's true. What we also consider and understand that in general, the protocol for execution sharding actually doesn't really differ from interoperability between cross-chain protocols, but what we have stronger guarantees. So if we can align external chains with these guarantees, they can be a part of this interoperability protocol. That means that we can extend any on-chain application to this cross-chain model. Yeah. Any more questions, maybe? Or I did not answer something?
You answered.
Yeah, yes. Okay. Yeah, any more questions? Yeah, what I would like to add extra that recently I figured out one interesting concept that you can notice in Twitter a lot of projects that are focusing on scaling the networks. Yeah, like any single rollup, any single L1 chain talk about scaling. But the funny thing that actually no one talks about scaling applications. That's quite funny because once again, like consider what happens in the real world, because you have like CPUs and that actually also scaled a lot. You have ALU, you have pipelining, many features that actually scale like single CPU, but we don't have a single application who is running on a single CPU. And it's quite funny because, yeah, probably it also requires us to think about how we can scale applications and not only the chains, because finally we will end up with it. But yeah, it's just my notice. Okay, any more questions? Cool, in any way you can write me or like join our testnet and write in our Telegram chat if you will have any questions. Thank you once again.